Okay, let's first run the code one time to show you what it does. And then after it does that, I'm going to show you that you can actually, what happens when you remove related words. So you can just remove it and see the score will go down. So here we're removing that part of the code. So now here you just have the code without related words, and you're going to see the score is going to go up by about 600. Now, if you want to remove the priming, it will look like this. And that will go up by about 500. So now you, oh, did I not remove them, did I? I'm checking, I think I did it right. Oh, I didn't remove this part, but it didn't change it. But if I remove it, then it becomes like that. And so this is just the saving. And then here you have the searching. This just breaks early. If it didn't find it, it's not going to find the rest of it. This brings you to the next node about searching. And of course, the save, they need to search to save. So it's utilizing this here. When other searches go and search, they're just searching, they don't save. But those get the predictions. So they run through this again too, but they don't go through here. They just go through here now, and they can get well, you got the next words already. It brings you to the node, and then what happens is that you already have the next words really, but when you go through here now, you're allowed to, you can now use that node for the next words that you have. You can now use it and merge the predictions, the sets of them, to get one set of predictions. And so I think that's it. You can now just remove this then. You can remove some of these storage here now too now. And so that's how it works. So here's the algorithm. First it opens the data, and then in a loop we're going to go through all the code, looping it. It's building a tree. So it's going to take each search. This one is for tree 1, it's saving, it's a search that saves. So we're going to build the tree. It's going to take the last, it's moving a window along the data for 15 words. It's going to save every 15 words from the data and do a tree using this code, saving into the tree to build a tree. It tells you how many times any 15 or even 2-word exact match occurs in the data set. So you give each part of the tree a counter to tell you how many times it was seen. And then these are just some conditions for the code. We have a few other trees being built. Those are for gap matches, like I was walking down the street, but you actually see in a new input, I was jogging down the street, so it's still able to match in those trees and get the next words. So these are just, each search goes through the code, and these are just saving to make the tree memories. You have searching a tree here also. It's making a list for related words. And then after the searches are gone through the loop, you have more searches that search the tree, and those get the memories for what to predict next. So when we get to those don't go through this code. They actually continue down and will now enter this part for predicting. So those are different in that way, where the ones that save the tree enter this code, but they don't enter this part. So it switches now. So now they come down to here, and if it has an exact match in the tree, it's going to say, okay, what words come next? It gets those predictions, and it will do it for the last, if you give it a prompt of the last, if it finds a match of the last 2 words and 3 words and 4 words, it's going to get the predictions that come next after each of those matches of memory and mix them all into all, like say 5 sets of predictions into 1 set of predictions to get 1 set of predictions. That's this part here, where it's merging the predictions to get 1 final set. But before that, it is, for a few of them, it is looking at the last 500 or so words and then priming them. That's what this code here does, so that if you see dog a lot, you're going to predict dog then more likely. And so that's what this is doing. And then this part here is taking the predictions and evaluating. So it's generating the score for the evaluation of how accurate you are. So that's the predictions, and then evaluating for each word in the data set. It's summing them up to get the final score, and then it prints the score. Now the exact way that the related words work when it's saving it is it's going through its own tree that we stored. I think it's right here, and then it's a small miniature tree just for 2 words for now to test it out, and it's searching it, and what it's doing is it's got a list it builds too right here, and that's where the relations are stored. It does this only like once every 1,000 words right here. Is that code. And then what happens is that it starts with if we have a tree where you have like, it goes through the data and it takes like dog ate, dog slept, dog walked, and cat slept, cat walked, cat ate, cat died, and it switches them around so that you're storing into the miniature tree died cat, slept cat, walking cat, so they're backwards. This is so that when it's going through searching the miniature tree, it starts with the proofs, like both dog and cat share died, or ate or slept or walked. So it's going to start with those like walked and died and ate. So then it's going to go from the root of the tree and go forward to the actual words that might be related. And that's where you got the shared word, and then it's saying, okay, dog and cat, it's going to go like, say, from walking, and then after that you have dog, cat, horse into the miniature tree, in the miniature tree. So it's going to give each one of those in the list, each to each its own tally score there. You're building a part of it so far because you got to go through all the tree. So it's going to give them each, because they share a little bit to each other. You're looking at how many they share here. So what it's doing is it's saying, okay, you got walking dog 4 times and then walking cat 2 times. So they share 2. But first you have to normalize it, because if you have cat is 10 times rarer, then you have to artificially fluff it up so that you can correctly match it. So then you really got walking cat not 2 times, but then you have 20 times. So then you got 20 for walking cat and then 4 for walking dog. So now they actually have 4 really. So you're going to do that here is that you got 4, and you're going to store that into the list here. So that's done here when you store it. How many they share. So it's 4. You pick it's picking it here, the minimum. So it's 4. Yeah. And then, so you're looking at how many cat and dog share, total of how many they do have. And so now what you also do is if cat and dog share like 400, and you going to, and then here's dog and cats, how many times each dog and cat is seen in the entire data so far. So if dog is like, well, they're both normalized now, so the same number. Well, these give you the two, what they are. Cat might be 400 and dog might be 800, but you've already artificially made them both 800 by doing your code here. So what it's doing is it's just going to pick 800 here, whichever one it is. That's what max does. So if they both share 300, then it's 300 divided by 800 to tell you how much they share of the total max that they have. So it tells you how much they share of how many they do have. What word comes next after them? So that gives you the score, and then the amount just tells you it might lessen it if they're common words. So amount comes from this here, where if you're currently saving the score here for walking, the proof of called walking, say, then it's looking at walking, it's saying, okay, it's somewhat common, it's a little bit rare, because if dog and cat both share the, or along, or near, those are common words, so it's not going to help score it much. So it'll be like score times 0.2, so it's not going to come out as much when it's storing that part of the relation score. So if it's biting's a rare word, and it will make it a higher amount there. So that's just the related